In this video, we're going to do an introduction to exponential functions, and we're going to go through their defining characteristics, and we're going to look at how to do some transformations of exponential functions. So exponential functions is probably something new for most of you in your studies. You've probably heard tell of them, maybe seen graphs of them, but haven't done a whole lot of specific properties and shapes and that type of thing with exponential functions. There's a few key terms down here we'll talk about. We'll talk about what an exponential function is. We'll talk about exponential growth. We'll talk about half-life. We'll talk about an exponential equation. But the first thing we're going to get into are just some of the properties of an exponential function, what these functions look like and their functions look like. So an exponential function is going to be a function of the form y equals, and then there'll be some number. So c here is going to have to be an element of the, I'll say the real numbers, but there are going to be some stipulations. So this c is a number. However, in exponential functions, it has to be a positive number, and it can't be 0. So your base in an exponential function must be some positive number. Now, it can be decimals, it can be fractions, but they just have to be positive. So that's why we say real numbers, because sometimes students will, why don't you just say whole numbers, because then you don't get into negatives. Well, the problem with whole numbers is they don't include the fractions in between everything. Now, just to go back here, this is some properties. This is a screen capture right out of your textbook. Exponential functions will be of two forms. This type here, which you see, is what we're going to refer to as growth. So this would be exponential growth, which essentially means as the x values get bigger, the y values on your function get larger. This example is what's called exponential decay. This would be an example where as the x values get bigger, the y values on the function get smaller. Now you'll notice out here that it's kind of hard to tell perhaps from looking at the image, but what's going on out here and here is what's called an asymptote. That's probably a new term for most of you. However, it is a term that you'll run into a fair bit in other areas of math and calculus as we continue down this journey of pre-calculus and calculus. So an asymptote is a line that a graph gets closer and closer to, but never actually touches that line. So we'll kind of talk a little bit more about those as well. So the c here, or the base, and this one is 2. The base in this one is 1 over 2. So you can see the difference here. If your base, c, was more than 1, we got growth. If the base was between 0 and 1, you end up with what's called decay, or a decreasing function. If the base had actually been a 1, if you think about this, if you had 1 to the x, it's neither one of these situations, because 1 to any power would have just stayed a straight line across through y equals 1. So it doesn't model exponential behavior. So your base cannot ever be 1 either. I should have maybe stipulated that up in the beginning, up here as well. So when you're talking about your bases, they have to be more than 0, but your base cannot be a 1, because 1 has that unique characteristic of 1 to any power stays 1. What else do we got? So the domain of these, x could be any number. There's no reason you couldn't pick any x value. The range of these two, all the y values are going to be above the asymptote line. Now notice there's no equal sign here, because the function comes down and gets closer and closer and closer to this line, but never really touches it. So the asymptote is y equals 0, which if you look at this graph, all the y values are above 0. Same as this one. All the y values are above the horizontal line, y equals 0. For that reason, the y-intercept of any exponential function of the form y equals some base to the x is always 0, 1. Now you may say, well, why is that? One of the things we did in our study with exponents is we should have realized that if you have any base, This is your x. So when you're finding the y-intercept, you're letting that be 0. Well, any base to the 0, we know is always equal to 1. So therefore, 2 to the x, 3 to the x, 5 to the x, 1/5 to the x, 1/10 to the x, they're all going to pass through this ordered pair called 0, 1. So because it's such a common point to all of these exponential functions, it has a special name. It's called the focal point. Okay, so focal point is that ordered pair 0, 1, which all exponential functions will pass through, provided there's not any other transformations, which you're going to see what that all means later on when we start adding the transformations we studied in Unit 1. We'll do the transformations of these functions in the same manner. So I mentioned already, that means they wouldn't cross the x-axis, so there's no x-intercept in this case. And the horizontal asymptote, that's the line you're getting closer and closer to, was y equals 0. So I showed you here the only real point that these shared was the 1, 0, 1, and it had a special name called the focal point. I've already mentioned, so when I say c is greater than 1, I'm talking about this type of a function. So c, this letter doesn't, sometimes we'll use c, sometimes we'll use b. It doesn't really matter. The base. If the base is more than 1, you're going to get a situation involving exponential growth. So some examples of that would be investing money is an example of exponential growth if you use compound interest. A bacteria that's doubling every so often, or the way that bacteria grow is called exponential growth. Exponential decay is when the base, so you still have y equals c to the x, but your base is somewhere between 0 and 1. So it's a decimal like 0.75, or a fraction like 3/5. That is some value between 0 and 1. Well, then you're dealing with what's called exponential decay. And it would be that pattern where it's coming down this way instead. A couple of examples of that would be if you buy a new vehicle and you go to trade it in the year and it's lost value. So you paid $75,000 for it. 1 year later, you go and try and sell it, and they're only going to now tell you it's worth $55,000. Well, that value you've lost is called depreciation. Radioactive elements will decay. So a common one is carbon-14. That's one used in carbon dating. Carbon-14 will, if it's just left to sit in the atmosphere, it will decay, and it has something called a half-life, which we'll get into later on in the unit, and that'll tell you how long it takes for that carbon to decay to a certain quantity. Okay, so that's just some kind of background terms and facts that go along with exponential functions. Let's now look at let's look at horizontal asymptote and y-intercept a little bit more carefully. So I've already mentioned what a horizontal asymptote is. So this is kind of a written out definition. It's a horizontal line that a graph approaches, but never, I said crosses. Intersects is another word that means crosses. So if I looked at these two functions, as we've already mentioned, they both have the horizontal line y equals 0 that they get closer and closer to, but never cross. Now, if I was going to look at transformations, so I was going to take this graph and think of transformations, reflections, stretches, and translations. So reflections is when you can reflect it across the x-axis or the y-axis. Stretches is where you can stretch it either vertically or horizontally. And translations would be when you take your graph and physically move it up or down, or you take your graph and move it left or right. So if you were going to think of all of those transformations, for example, let's take a reflection. Well, a reflection would just take this graph. So if you reflected it across here, it would just turn it so that it would go through that point. It would look like that, but it's still going to get close to this line. If you reflect it across this line, it's going to turn it down this way, but the asymptote didn't move. So for reflections, the asymptote's not going to change. Well, what if I stretched it? Well, all stretching does is make the y values increase faster. It's still going to go through this point, but it might look like this, and it might come down here quicker, but it's still going to get closer to that line. If it was a horizontal stretch, it might stretch it out this way, but it's still going to get closer and closer to the same line, y equals 0. So reflecting and stretching had no bearing on the horizontal asymptote. Well, I say, let's start looking at translations then. If you took this graph and just slid it, let's say left, okay, 2 units left. Well, everything just moves 2 units left. This goes here, but you still get the same shape. It's just moved over, but it's still going to only get closer and closer to this line. So moving a graph left or right is going to have no bearing on the horizontal asymptote. Well, of course, I've left the one that does till the end. The only transformation that you would ever do to a function that would change, sorry, of an exponential function that would change the horizontal asymptote is a vertical translation. So if you were to take this function and move it up or down, so let's suppose I move it straight down, well, you can see what's going to happen. You're going to take this function when it moves down 2, let's say I pick down 2, pick any number. Well, down 2, it's going to take this graph and physically move it down 2 units everywhere. Everything's going to move down 2. Well, instead of getting close to this line, now it's going to get closer and closer to this line. So your graph's going to come down here. So it's going to go through there. That's going to look, I'm not being overly precise with these, but you're going to get the idea. It's going to come out and get closer and closer to this line, which is now, instead of y equals 0, now it's y equals -2. Well, this number, -2, corresponds with how far I moved down. So you could imagine if I took this graph and said, well, shift it up 4 units. Well, instead of this line being y equals 0, I think we can use our reasoning ability to say, well, now I'm going to move that up 4, 1, 2, 3, and your horizontal asymptote is now going to be here. Your graph's going to come down and get closer and closer to this line instead, which will now be y equals 4. So the translation that is going to be key in the horizontal asymptote, which is a key point or a key kind of focal point of interest. Focal point's not a great word because that's this number up here, is going to be the horizontal asymptote. So it's important that we are going to be able to identify that, and hopefully you can see that it is tied in with your vertical translation. I compare it to the sinusoidal axis in your last unit on graphing trig functions. Kind of the same idea. If you move your trig function up or down, it moves your sinusoidal axis. If you take an exponential function and move it up or down, it is going to move your horizontal asymptote. Right? Y-intercept is another key point that is often asked of students to identify. Well, if you just go back to your work on y-intercept from any function, even grade 10, y-intercept is found by making the x equal to 0. So all I would have to do is go to this function. If I said, where's it crossing the y-axis? Well, let's find out. Let x be 0. 2, 3 to the 0, minus 5. Anything to the 0 is 1. This graph is crossing the y-axis at -3. Versus you have a base function. So the base function in this, so what do you mean by base function? Think quadratics. When we did the whole left, right, all that good stuff, well, the base function was y equals x squared. When we did sinusoidal relations, our base functions were either sine of x or cosine of x. Well, in this function, you're going to have a base exponential. This is your base function, 3 to the x, which if you had a base function, it's always going to go through 0, 1, because your base function is always some number to the x. Could be 3 to the x, 5 to the x, 1/3 to the x, 1/4 to the x, but it's some number to the x. And that's how you get your y value. Well, if I just take a look at these functions down below here. Now, one of the common things asked to identify with exponential functions, like any other function, is the domain and range. The domain is always easy. X can be any number you want it to be. There's nothing you would fill into an exponential function that's ever going to cause any issues. So your domain is always that. It's one of those gift questions, right? There's no number I could put up here. It could be a decimal, it could be a fraction, it could be a negative. You can have negative exponent, you can have zero exponent. So whatever you're filling in here as your variable for X, there are no limitations. It could be any number. Now, the range, because you know that exponential functions are going to, or you're learning, probably don't know yet, but they always look like this. This, or this, or this, but they have this general kind of exponential shape to them. What happens though is that every single one of them will have a horizontal asymptote, which depending on whether your graph looks like I've drawn here, well then the y values are always going to be above the horizontal asymptote. So if I looked at this one, based on your knowledge of transformations, and we're getting a little ahead, not ahead of ourselves, but we're relying upon your knowledge from Unit 1 in the course on functions. This number in front of your function would be a vertical stretch, just like in a trig function where it represented a change in the amplitude. It's stretching it vertically. This is a vertical stretch. This is your base function, 3 to the x. So if I ask you, what do you think minus 5 is going to do? Well, say I'm not sure. Well, if you're not sure, I have it opened up here already. Here's the graph of 2 to the 3x minus 5. So if you look at this graph, it's getting close to, I know it looks like it's blending right into, but it's not. If you were to zoom in on this, it's getting close to this line, right? This isn't let me write on here, but it's getting close to the line minus 5, which corresponds with a vertical shift. It took the graph 3 to the x, it stretched it vertically by a factor of 2, and it moved it down 5. So therefore, all the y values are above negative 5. Let's have a look at that back here. So all the y values are bigger than negative 5. That's your range. As I said, our domain, no restrictions. X could be any number I want it to be. What if we put a negative out here? Now again, if you would completely come into this blind without any knowledge of functions and transformations, it might be a bit of an issue. But we're supposed to know that if you put a negative here, that reflects a graph. It's a reflection. And you're supposed to know which axis that reflects it in. A negative out in front of your function here reflects it in the x-axis. Now you say, what does that mean, reflected in the x-axis? There's a graph. This is that same graph reflected in the x-axis. Looks like that instead. Well, let's think about this. If I had this, I'd say all the y values are bigger than 0. But if I flip that over and make it go down here, well, now all the y values are less than 0. So you've got to consider here that this has been reflected. So if you look at this, without me, I'm going to show you the actual graph here in a second, but if we think about it, say, well, in this one, all the y values are above negative 5. But in this one, we're going to flip it over. Well, that means all the y values are going to be lower than negative 5 now. So, is our assumption right? Let's have a look. So if I'll just sketch it on the same axis here. So y equals, put a negative 2 out in front. Base is 3 to the x. And then we're going to move it down 5. And you can see it's the same graph, it's the blue one, except now all the numbers on this graph are below the number negative 5 instead of above the number negative 5. So that negative just changed my range to y is less than negative 5. All right, so if I'm asking you for the range, it's going to hinge upon the asymptote and whether or not there's a reflection. Those are going to be the two things you're going to have to consider. Okay, so if I just have this quick chart, we'll go through and I'll fill these in. So we're going to look and determine whether each of these functions would be what you would consider to be a growth or a decay. We're going to identify what the y-intercept would be, and we're going to figure out what the horizontal asymptote would be. So the first thing, let's do growth or decay. Growth or decay depends upon the base. The base function here is 5, and it's raised to the x, so that would be an example of growth because the base is more than 1. That's all you look at. Y-intercept. To find the y-intercept, you let x be 0. So easy ones here, I'm just going to do them in my head. 5 to the 0 would be 1. Multiplied by 3 would be 3. Take away 4, the y-intercept, x would be 0. Y would be -1 in this graph. The horizontal asymptote always goes with your vertical shift. So it would be y is equal to -4. Doesn't ask for the domain and range, but the domain is always x could be any element of the real numbers. I'll just scribble it here. This graph, because there's no reflection, all the y values would be greater than -4. This time my base is somewhere between 0 and 1. That's an example of decay. If I let x be 0, anything to the 0 is 1. Multiplied by 4 would be 4. Add 1 would be 5. 0, 5. This +1 is going to move your graph up 1. So the horizontal asymptote would be y equals 1. Didn't ask for domain and range, but let's write them out. X could be anything. In this case, there's no reflection, so all the y values are going to be above the horizontal asymptote of y equals 1. So it's greater than that number. 2 to the x minus 2. Your base is 2. That's growth. What is the y-intercept? So if we filled 0 in for x, 2 to the 0 would be 1. Subtract 2 would be -1. You have a vertical shift of down 2. Your horizontal asymptote is y equals -2. X could be any number. All the y values, there's no reflection, would be above your horizontal asymptote of -2. Base is somewhere between 0 and 1, so this one's decay. If I wanted to get the y-intercept, I would let x be 0. 1/2 to the 0 would be 1, so this whole thing becomes 1, multiplied by your coefficient 3/4, 0, 3/4. Notice there's no number out here, so your horizontal asymptote would be y equals 0. X could be any number. No, none of these have reflection, so there's no reflection again. All the y values are above the horizontal asymptote. And the last one, base is 3, so that's another growth because it's more than 1. The y-intercept, I let x be 0, so it's 3 to the exponent 0, which would equal 1. Multiply that by 5 is 5. So across at 0, 5. Again, like the last one, there's no number out here, so it would also be y equals 0. X could be any number, and all the y values have to be above that asymptote. So that's just quick ways to identify horizontal asymptote and y-intercept and determine whether you're dealing with a growth or a decay function. All right, so now we're going to kind of go back to all of our transformations like we would have done in Unit 1. I'll just quickly refresh your memory on what they are. So the number in front of the function, that's for two things, reflection and vertical stretch. The number in here in front is for horizontal reflection. Actually, this one's for reflection in the x-axis. This one is a reflection in the y-axis, so side to side. And it also is your horizontal stretch factor. Remember this one, I'll put it together here in a second in our mapping. This one here is always the reciprocal. So if you saw a 2 there, that means it's going to be half the width horizontally. If it was a 1/5, it's going to be actually get wider by a factor of 5. This one's always the reciprocal. This number here was your horizontal translation. So moving the graph left or right. Also remember this one if it's a plus. So if that's a plus C, it's actually going to move your graph left C. So your vertical stretch here would be 1 over b. This one would be, if it's a plus c, would be left c. Left c. And this out here is your vertical stretch. Sorry, not stretch, vertical translation. That's where you take your graph, don't change the shape of it, move it straight up or down. And a plus d would move. So if I use this as my kind of model, this would be moving up d units. These transformations, as you're hopefully figuring out, they apply to any type of function. We apply them in general in the first unit. We looked a little bit at quadratics kind of as a model, but it doesn't matter whether you have a quadratic function. We did the last unit, we did trig functions. We had sinusoidal relations where we could tell whether the sinusoidal was getting stretched, flipped, all that good stuff. We were using this same knowledge. So we're going to use the same thing again in this unit to determine what is happening to exponential functions. So if I look at my next slide, I've kind of got it laid out a little bit more detailed here to pertain to an exponential function. So you could have a number in front of your exponential function. Let me just back up for a second. If you were to look at all of this, and I said, what's the base function here? Well, in this example, the base function will be y equals whatever that number is to just the power of x. Now, I know there's a bunch of other stuff here, but they're called translations. So we're going to figure out what effect those are going to have on our graphs. Well, thinking about just regular function transformations, this number in front, the a, it is a vertical stretch factor, and it also controls whether there's a reflection in the x-axis. So a negative here would make this flip across the x-axis. Also remember your acronym from Unit 1. This is always the order you consider transformations. Reflections always first, then stretches, then translations. B is your base ratio, your common ratio, they'll sometimes call it. C is a horizontal stretch factor. Now this is up in the exponent. We'll see this when you see a numeric example in a moment. But that number there, when you go to identify your horizontal stretch factor, it's the number in front of the x. It also controls whether there's a reflection across the the y-axis. If that had been a negative, then this graph would flip side to side. So for example, if you had this, which was y equals, let's say, 2 to the x, and then I said, well, what about y equals 2 to the negative x? That's a negative in front of your x. That flips it. So this is going to go here, and this is going to go here. The graph would look like this instead. So it switches from growth to decay. So again, when you get negatives on the go here, you got to be careful. There's more to look at than just the base. Like that first chart we did was really, really easy because there was no reflections. But when you start putting reflections into play here, you got to consider things more carefully to determine whether you've got growth or decay. What else? So we said that's our horizontal stretch factor. It would be 1 over c. And our reflection in the y-axis could also be controlled by that one as well. Okay, so just, sorry, I got interrupted for a second. I'm back here. So as I said, this one controls your horizontal stretch factor. It's always the reciprocal. This would be your horizontal translation. This would move your graph left or right. The one thing you got to watch for is that you always have 1 as your coefficient of x before you identify your horizontal translation. It's the same as with the trig functions. When you had like 2x minus 60, you had to factor the 2 off. So even though it said minus 60, it wasn't going right minus or 60 units. It was going right 30 because you had to factor the 2 out first. It'll be the same with these. You'll see when I get an example with numbers in it. And then, of course, the number out at the end is your vertical shift up or down. If I was going to write a mapping for this using what you see up above, if I had, so I should get them both. Maybe I'll just switch so we can full screen this and see everything. There we go. So looking at this, if I was going to write a mapping, so the C will control how it's stretched horizontally. So that affects the x values, and it's always the reciprocal. So it's going to be 1 over c multiplied by x. Now, if that was a negative, it'd be negative 1 over c times the x value. If it's a subtract h, it's going to move to the right h, so it's going to be plus h. These are always the opposites. The number in front, your vertical stretch, goes with your y, so it's a multiplied by the y. If that was a negative, it would be the negative number times y. The negative would switch all your y's from positives to negatives or vice versa, and that will give you that reflection image across the x-axis. And then you have your plus k, which would be added to your y values to move them up or down. If it's a plus k, it's a plus k. If that was minus 3, it would be a minus 3 here. Again, the same as you've done already in 2 prior units. So this is going to go very quickly, we hope, because it's dealing with some of the same background information we've already been using. Okay, so let's have a look at this one as an example to start. And if I wanted to fill this chart in here, the only thing I'd notice that it's not in its general form is this right here. It should be 4 onto x minus 3. So I do that always because you want your coefficient in front of your x when you do transformations to be a 1. Right? You want that to be always a 1. So now we look and say growth or decay. Well, I look at the base, which would indicate growth because it's more than 1. There's no reflection, so it's still going to be growth. Because if it was growth and got reflected, then you got to be careful and look at it more carefully. Equation of the horizontal asymptote is always this number right here. And don't just write 7. It's not 7. It's y equals 7. The domain, well, there's your gift. It's always the same. X is known with the real numbers. The range, all the y values are always, if there's no reflection, they're always going to be above the horizontal asymptote. So that would be y is more than 7. The y-intercept in this one is going to be a little bit uglier because I'd have to, if I let x be 0, the y-intercept, just put some scribbling here, would be 3 onto 5. Now, if x was 0, it's going to be 5 to the negative 12 plus 7. So if you were to take that, I'm only going to give you a scientific notation because that's going to be 5 to the negative 12 is 1 over 5 to the positive 12. And that is a really small number. So let's see what happens here. 3 times 5 to the exponent negative 12. And then if I add 7 to that, I get 7 with a whole bunch of zeros. So my y-intercept is 7.00. 1, 2, 3, 4, 5, 6, 7 zeros. And then I got 1, 2 at the end. There's your y-intercept. So that's where it's crossing the y-axis. A mapping rule. So the mapping rule that would map this function would be xy mapped to. So that number, take the reciprocal of it. So it's going to be a quarter of all the x values. They're going to go right 3. I'll move them right 3. We're going to triple all the y values, stretch it vertically by a factor of 3, and we're going to move the y values up 7. And then it says, where would the new focal point be? So your base function is 5 to the x, which would pass through 0, 1. It's saying, where would that point end up? Well, you just take 0, 1, and you put it through your mapping and see where it now sits. So if x was 0, it's going to be at 3. And if y was 1, it's going to be at 10. This would be the new focal point after you do all the transformations that were shown in this function. Okay. Now, this one is going to be similar, but it's going to require us to do some rearranging first. So we're going to have to get it into that nice format of y equals. Well, if I take this function and try and get the y equals here isolated, well, you got to get rid of this 2/3 and you got to get rid of this 3. So you can either do it at one time, or you can kind of slowly chip away and get rid of things one little value here at a time. So some students say, oh, I want to get rid of the 3. Okay, let's multiply both sides by 3. That will get rid of the 3. Now that takes care of the whole left side. When you multiply this side by 3, you'd multiply the coefficient. You never touch the base of your function because you'd be breaking order of operations. If you multiply here, you're multiplying before you deal with an exponent. You can't do that. And then you'd have to multiply this by 3. So now you're down to 2 onto y plus 3 equals negative 6, 5. We might as well factor this. Remember, it's got to be 1x, so it's 2 onto x plus 4. And then this will be 18. So that's getting rid of the 3. Then I'm going to get rid of the 2. So I'm going to divide everything by 2. Divide this. Now this is all considered 1. And this be considered 1. Let's go up here. So it's going to be y plus 3 is equal to, and negative 3 has no effect on your base. It stays the way it is. So 5 onto 2 onto x plus 4. And this will be plus 9. And then the last thing is subtract 3 from both sides. So when you subtract 3 from here and subtract 3 from the right side, you end up with this function. Negative 3, 5, 2 on x plus 4, plus 6. Now, some students struggle with that part of the question. That's got nothing to do with exponential functions. That's got to do with your ability to rearrange a function, which, again, that's a skill we have to have if we're going to be able to do these types of questions. You could have got rid of the 2/3 all at once by, instead of multiplying by 3 and then dividing by 2, if in the beginning you could have just multiplied everything by 3 over 2, would have accomplished that as well. Okay, so now that I've got this in this nice y equals form, we can fill in that chart like we did in the last one. You gotta watch this one. It looks like growth. So if you think about it, it's gonna be that. It's growth because of the 5 being your base. But the negative here is gonna flip it and turn it down this way. Well, now the x's are getting smaller as the y's, sorry, the y's are getting smaller as the x's are getting bigger. That turned it into, because of this, decay. That's one that a lot of students just quickly look only at the base, not worrying about reflections, and then all of a sudden they're getting this to be the backwards of what it should be. Horizontal asymptote. Easy enough. When you get it to here, it's y equals 6. The domain, there's your freebie, it's always this. The range. So normally the y values are always above the asymptote, but because of this reflection in the x-axis, you can see my demonstration here, well, it's going to flip it. All the y values now are going to be lower than the horizontal asymptote. Our y-intercept here, let's see what happens. So if I put 0 in here for x, I'm going to get y equals -2. So 2 times 0 is 0 plus 8, so it's going to be 5 to the 8. And then I'm going to have a plus 6. So again, this is going to be probably a bigger number this time because it's not a negative exponent, so it's going to be 5 to the power of 8. Multiply that by -2, and then add 6. I get negative 781,244. And the good news is we don't have to draw this, so we don't really care about how ugly these numbers are. If we had to draw it, then I'd be a little concerned about that. Mapping, so let's write a mapping for this function. X, Y will get mapped to, so let's start with our x, so it's going to be half the x's. They are going to go left 4. We're going to multiply the y's by -3. And so that'll reflect them and stretch them, and we're going to move them up 6. Now this shouldn't say 5 to the x anymore. Oh, yes, it is. It's still 5 to the x. So our base function is 5 to the x, which would have the focal point 0, 1. It says where would the new focal point be? So you take 0, 1 and you map it through your mapping. So if you put 0 in for x, you're going to get -4. And if you put 1 in for y, you're going to get +3. So there's where the new focal point would end up after you sketched it. This one, they start with the mapping. And again, it's using 5 to the x. This could be any function, 3 to the x, 2 to the x. It's done the same way. It says, what would be the equation of this function? So it's kind of basically putting your brain in reverse. Let's start with that. Y equals. Well, if you're going to multiply the x values by 5, that means that you must have had, and it says it's base 5 function, so it's 5. The only way you multiply by 5 is if you have a 1/5 here. Then they're going right 4, minus 4. You're multiplying the y values by a -2, and then you're moving them down 3. So that's us being able to go in both directions. Have this function and turn it into a mapping. Having said that, if you have the mapping, you should be able to turn it into a function. What is the y-intercept? Well, the y-intercept here is going to be, let me see here, so x is going to be a little bit ugly because if you let x be 0, so the y-intercept, I let x be 0, it's going to be, use your function, so y will be -2, 5. This is 0, so it's going to be to the -4/5 minus 3. So we're going to get a decimal. Okay, so if I just put this in my calculator, -2, 4/5, sorry, not 4/5, -2, 5 is your base. With the exponent -4/5. Make sure if your exponent is a fraction, put it in brackets. And then subtract 3. -3.552. So y is -3.552. What's the equation of the horizontal asymptote? There it is. The horizontal asymptote would be y equals that number, -3. It says the ordered pair 3, 125 is on the original function. And do you agree that that is an ordered pair on the original function? Some of them say, I don't know, where'd that come from? Well, think about it. If x was 3, this is your base function. So if you have y equals 5 to the x, and I said x is 3, well, yeah, 5 to the power of 3 is in fact 125. So yes, that was a 3. You would get 125. So 5 to the 3, y would equal 125. So the ordered pair 3, 125 is on the base function. Sometimes they don't give you these. They say find 3 function or ordered pairs from the base function and translate them to the new function. Well, there's one. Well, you make them up yourself. If your base function is 5 to the x, let x be 1. You'd get 1 comma 5. If x was 2, you'd get 2 comma 5, 25. If x was 0, you'd get 0 comma 1. It could be negatives. If you put 5 to the -1, the y value is 1/5. So you can make these ordered pairs if you need them. So then it says, well, where would this new point be? So this is from your base. Where would this be after you do this? Well, you just fill it in. 5, x is 3, minus 2, y is 125, and it's going to move down 3. So this ordered pair is now going to be at 19, -253. That would be where this point 3, 125 would have ended up after you applied all these transformations that were identified up above. This just kind of shows you what I was talking about a moment ago. If you have y equals 7, 2, this is an exponent, the exponent 1/5 x plus 3 plus 4, and you wanted to do a mapping. Well, the mapping, let's see, I'm going to multiply the x's by 5, I'm going to move them left 3, I'm going to multiply the y's by 7, and then I'm going to move them up 4. So if that's the case, multiply the x's by 5, move them left 3, multiply the y's by 7, and move them up 4. So that's what I said. That's my mapping. I was going to say, well, how do I get points? Well, you make them up. You take x values, look this over and say, what's the base function? You can tell by looking at this number right here. So this base function would be 2 to the x. So now it's saying let x be some different numbers. So you pick them, doesn't matter. If x was -3, 2 to the negative 3 is 1 over 8. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. I know sometimes this person will say, what? Where's he getting that from? You have to understand negative exponents. 2 to the negative 1 means 1 over 2 to the positive 1. 2 to the negative 3 means 1 over 2 to the positive 3. This would be 2 to the 0, which would be 1. 2 to the 1 would be 2. 2 squared would be 4. 2 cubed would be 8. And then if you were going to graph it, I'm not going to go through all of these, but you would take, let's pick a couple. Let's pick, just keep it easy, let's pick this one. So where would 1, 2 end up? Take x as 1 and put it in here. 5 times 1 would be 5. 5 take away 3 would be 2. Put 2 in for y. 7 times 2 would be 14 plus 4. You'd do that. You'd do that for a series of points, and then you'd plot these new points, and that would give you what this graph would look like. And that's how you use mappings. Again, it's very similar to trig functions where you used your quadrantals, 0, 90, 180, 270, 360. You got the y values that went with them, and then you map them to get the new points. Same thing, just exponential functions. Good news is we don't sketch these that often, so you don't have to worry too much about it. But that's how you would do it if you had to draw a sketch. Okay, so let's look here. I think I got a couple more examples. We pretty much got all the material covered, just a matter of doing a couple more practice ones. So if I had this question and I wanted to figure out, what does it want here? Where would the point 4, 81 now be located? So the first thing I need, then it tells us here we need a mapping. Try and make this a little bit better to see. If I was going to do that, the first thing I'd want to do is get y equals by itself. So let's, in this example, start by getting rid of the plus 7. Now students say, could I divide by 4 if I wanted first? You could, but that's going to bring in these ugly fractions for now. So I think the first thing I would do is get rid of this plus 7. Just subtract 7, and then you're down to 4y equals 8, 3. Got to factor out the 5. So this is going to become 3/5. And minus 13 minus 7, that'll be minus 20. Now I'll divide by 4, and you'll get, so this is all considered 1 because they're multiplied together. Divide by 4, divide by 4. I'll just go over here. So here's your final answer. Y would equal 2, 3, 2 to the 5, so it's x minus 3/5, and it would be a minus 5 at the end. So my mapping, xy, would map to, I'd have to take 1/5 of my x values, 1/5 of my x values, move them right 3/5. Then I'd have to multiply all my y's by 2, move them down 5. So it says, where would this point end up? So where would 481 end up if you put it in here for x and y? So it's going to be 1/5, x is 4, plus your 3/5, comma, 2, y is 81, and then subtract 5. So it's going to end up at this new ordered pair. This is 4/5 plus 3/5. So 7/5 would be the x value. The y value is going to be 162, subtract 5, 157. And then every once in a while, we'll throw this at you to try and make sure you remember some things from Unit 1. What would be the coordinates of any point on the inverse of this function? Well, this point is on the function. So the key to inverses, if you can remember from Unit 1, switch your x and y coordinate. So because I've got a point already on the new function, to get a point on the inverse, you just switch it. It'd be 157, 7/5. And that would be a point on the inverse. Okay, so remember, inverse go through your whole transformation first, get the new coordinates on the function with all your transformations, and then switch your x and y's at the end. I think we did that one already, so I think we did one with different numbers. This is from your textbook. It just kind of goes through all the things that I've been talking about. It shows you what happens when there's a number here for all your transformations, up, down, all that good stuff. So again, if you wanted some notes to have, I'm not going to go through all this again because I've talked about it all already. And this says checkup time. So this is kind of our last question where I put everything together, and let's just see how we would make out with it. So now this might be a good spot if you're at home. And you say, okay, did I understand what he just talked about? Pause your video, go through and answer all of these questions. Once you think you have some answers, I did change this over here to make it work a little nicer for us. I changed that to 5x plus 15 if you have a hard time saying what that's supposed to be, just so I don't get fractions. And then go through and answer this series of questions. All right, so use it as a checkup for yourself. Once you have some answers, put the video back on and see how you made out. Okay, so here would be your solutions. First thing you need to do is get this in y equals. Well, to do that, I would start by dividing by -3. So I'm going to work down here. So if I divide by -3, remember this, you never touch your base in that exponent. You're going to have 2y minus 5 equals, now it's a negative divided by a negative. So this is actually going to be positive 4 now. 2. You also factor out the 5 now. That'll be plus 3. And this will be subtract 3. I would add 5 next. If it was me. Add 5 to this side. Add 5 to this side. So we'll be at 2y equals 4, 2, 5 on to x plus 3, plus 2. And then last but not least, you must divide by the coefficient of the y to get it down to y equals. So divide by 2, divide by 2, divide by 2. So y equals 2, base 2, 5 to the x plus 3 plus 1. Okay, so that's going to be my first process, which that on its own is not easy. I get it. You have to have the skill set to do that. Now I'm going to go through and answer all these questions. So let me just get this color. So it says write a mapping that would map your base function 2 to the x. You know it's 2 to the x because your base is 2 here. What would you have to do to 2 to the x to turn it into this function as a mapping? Okay, let's go here. So my mapping. X, y would map 2. I'm going to take a fifth of my x value. I'm going to move it to the left 3. I'm going to double all my y values and move them up 1. That's the first item on the list they asked us to do. Done. State the equation of the horizontal asymptote. So the horizontal asymptote is always your vertical shift, wherever it has been moved to. So in this question, it is up 1, which puts your horizontal asymptote at the horizontal line y equals 1. That one's done. State the range. Okay, so it's always, all the y values are either above or below the horizontal asymptote, and that is dependent upon whether there's a reflection in your x-axis. This one does not have it, so that means it is going to stay above. So my range would be all the y values have to be above, greater than the horizontal asymptote of 1. I think next on my list was y-intercept. So y-intercept is found by letting x be 0 in your function here. So it's going to be y equals 2 onto 2, 5, 0 plus 3, 0 plus 3, fill in x is 0, add 1. Y equals 2 multiplied by 2 to the 15th power plus 1. So this is going to be a big number. 2, 2. So it's going to cross the y-axis at 65,537. So x is 0, y is 65,537. There's your y-intercept. So it says the ordered pair 0, 1 is on 2 to the x. Where would this, so that's called your focal point, where would it now be located? Okay, let's do that. Take 0, 1, and basically put it through your mapping. So over here, so 0, 1, and we're wondering where does it end up? Well, put it in here. So it's going to be 1/5 of 0 minus 3, 2 times the y value, add 1. So it's going to be at -3, comma 3 would be your new focal point. One more question they asked us was, determine the coordinates of any point that would fall on the inverse of this function. Well, this point is on the function, right? This one is on the new function with all the transformation. So on the inverse, the symbol for inverse is to the -1. You flip it around. Now let's suppose they said, because I think I've asked this before, I say without using the point 0, 1 as your initial point, determine some other point. So you can't use this one. Some other point that's on the inverse. So that will sometimes cause some confusion for students, but all you got to do is just pick a new point. That's why, well, how do I get a new point? Make one up. You know your base function is 2 to the x. So let's suppose I pick x is 3. Well, if x was 3, the y value, 2 to the power of 3, 3 comma 8. So 3 comma 8 is another point on the base function. So if I wanted to figure out where that point is, I could run 3 comma 8 through my mapping, right? So 3 comma 8. So where's that now? Let me go back up here so I can look at this. So 3 comma 8 will be 1/5 of 3. So that's 3/5 minus 3. 3/5 minus 3. Then put 8 in for your y value. And again, put in using the regular mapping. So if 8 was y, it'd be 2 times 8 is 16 plus 1, that's going to be 17. This is 3/5. 3 over 1 would be 15. So this would be 3 minus 15 would be -12/5, comma 17. Now that's on the function. If it said where would that be on the inverse, again, it just depends on how it's worded. On the inverse, it would be 17, comma -12/5. All right, so hopefully you're seeing lots of overlap here between our unit on functions, our unit on sinusoidal relations, and now how we're applying that same information to sinusoidal, or sorry, to exponential functions. Now we've got some idea at least what they look like and what we're talking about. All right, so if you need some practice on this material, I want you to go here in your textbook. There are some practice questions you can use. As always, there will be an assignment to follow on this material. And again, I know the video is long, so if you have to go back and kind of look at it in smaller chunks, that's fine. That's why you get a few days to go through this and kind of get your brain wrapped around it. Your assignment will follow until later on in the week. Okay, so best of luck. Any questions, please reach out, and I'll do the best I can to get you pointed in the right direction.